Hello and welcome. Have you ever had one of those days? You know the one. You spend all morning meticulously cleaning your room. Every book is on its shelf, every sock is paired and tucked away. The floor is clear, the surfaces are dust-free. It's a masterpiece of organization. Then you leave for a few hours. You come back and it's not quite how you left it, is it? There's a jacket on the chair, a few crumbs on the desk from a hastily eaten snack. The bed might be a little rumpled. Even if no one else has been in there, it just seems messier. It's taken a step, however small, away from that perfect order and towards a gentle, comfortable chaos. Or consider this. You're stirring a spoonful of milk into a dark, rich cup of coffee. At first, the contrast is stark. Beautiful, swirling white tendrils against a deep brown canvas. But you keep stirring. The white and the brown begin to blend. They mix and mingle, and soon you don't have two distinct things anymore. You have a single, uniform, beige liquid. Now, try to unstir it. Try to get those beautiful, distinct swirls of milk back. You can't, can you? It feels like the most fundamental law of the universe is preventing you. The coffee wants to mix. Your room wants to get messy. That feeling, that stubborn one-way direction of things, from order to disorder, from separation to mixture, from concentration to diffusion, that, at its heart, is what we're going to talk about today. That is the story of a concept so powerful, so fundamental, that it underpins everything from the fate of a melting ice cube to the ultimate fate of the entire cosmos. It's a story of brilliant, often troubled minds, of an idea born in the soot and steam of the Industrial Revolution that grew to become a cornerstone of modern physics, chemistry, biology, and even information theory. We are going to talk about entropy, and I promise you, by the end of our time together, that word will have transformed from a vaguely intimidating scientific term into a familiar and, frankly, mind-blowing concept. We will leave no stone unturned. We'll start at the very beginning, in the heat and clang of early steam engines. We'll meet the brooding, tragic figure who first gave it a name, and the relentless, mustachioed genius who saw its true, terrifying cosmic significance. We'll follow the thread to a man who, in his despair, may have taken his own life over its implications, and then to a visionary who connected it to the invisible dance of atoms. We'll even see how, centuries later, it was reinvented to help us send text messages and stream videos. This is a journey into the hidden arrow of time itself. So, get comfortable. This is going to be a deep, deep dive. But don't worry, we'll take it one step at a time, in plain, simple language. Let's begin our story not in a pristine laboratory, but in a world powered by coal and fire, a world desperate to understand how to get more work from its machines. Our story starts, as many great stories in physics do, with a practical problem. It was the 19th century, and the world was in the throes of the Industrial Revolution. Steam engines were the beating heart of this new age. They pumped water out of mines, they powered looms in factories, they propelled locomotives across continents. They were transforming society, but they were notoriously inefficient. A huge amount of the expensive coal you shoveled into the furnace was wasted. It didn't turn into useful work. It just heated up the surrounding air or the engine itself. Engineers and scientists were desperately trying to figure out the fundamental principles that govern these heat engines. How could you design one to squeeze out every last bit of work from a lump of coal? What were the absolute unbreakable laws of heat? This was the world of Sadi Carnot, a young French engineer. In 1824, Carnot published a slim but profoundly brilliant book called Reflections on the Motive Power of Fire. To truly appreciate the quiet revolution that was Sadi Carnot's book, Reflections on the Motive Power of Fire, we need to put ourselves even more firmly in the mindset of his time. The caloric theory wasn't just some vague idea. It was the established, mainstream scientific understanding of what heat was. Championed by the brilliant French chemist Antoine Lavoisier, the theory proposed that heat was a physical, albeit weightless and invisible substance, a fluid he named caloric. This caloric fluid was thought to be composed of tiny, self-repelling particles that would surround the molecules of a body. When you heated something up, you were adding more of this caloric fluid to it. The particles, repelling each other, would push the material molecules further apart, which perfectly explained why things expanded when heated. Conversely, when something cooled, it was losing caloric, and the molecules would draw closer together. It was a beautifully intuitive, if completely incorrect, model. Think of a sponge soaking up water and expanding. That's how scientists then imagined objects absorbing caloric. This theory was so dominant that it shaped every question a scientist would ask about heat. And it was within this intellectual box that the young Sadi Carnot began his own revolutionary thinking. Now let's get to know Sadi Carnot a little better. He wasn't just any engineer. He was the son of Lazare Carnot, a famed mathematician, engineer, and a powerful figure in Napoleon's government. This meant Sadi was born into a world of science, mathematics, and national industry. He was a brilliant student, graduating from the prestigious École Polytechnique in Paris, where he was taught by some of the greatest scientific minds of the age, like André-Marie Ampère and Siméon Denis Poisson. He then became a military engineer in the French army. However, his career was complicated by politics. After Napoleon's final defeat, his family fell out of favor with the restored Bourbon monarchy, which likely stymied his military advancement. This professional frustration, perhaps, was a blessing in disguise for science. Posted to various locations and feeling his recommendations were ignored, he eventually took a long leave and dedicated himself to private intellectual pursuits in Paris. There, he attended lectures on physics and chemistry and became fascinated by a pressing national problem, the inefficiency of steam engines. France, at the time, was lagging behind England industrially. English steam engines were more efficient, and there was a burning question as to whether there was a fundamental limit to how efficient any heat engine could ever be, or if French engineers just needed to find a better design or a better working substance than steam. Carnot, with his profound and systematic mind, decided to tackle this not as a mere practical engineering problem, but as a grand theoretical one. He asked a deceptively simple question: is there a universal principle that governs the production of work from heat, a principle that would be true for any engine, regardless of what it's made of or what's inside it? This was the genesis of his great work. In 1824, at his own expense, he published the results of his reasoning in a slim volume of only 118 pages, Reflections on the Motive Power of Fire. It's a book that would, decades later, be recognized as the founding text of thermodynamics. In it, he made his legendary water wheel analogy, which you mentioned. But let's linger on that analogy for a moment, because its brilliance and its flaw are both so important. Carnot, thinking within the caloric theory, reasoned that the work didn't come from the consumption of caloric, but from its transfer, its fall from a high temperature to a low temperature, just as a water wheel turns not from the consumption of water, but from water falling from a high place to a low one. The greater the height difference for the water, the more work you can get. Similarly, Carnot deduced, the greater the temperature difference between the boiler and the condenser, the more motive power you could extract from a given amount of caloric flowing through the engine. This was a monumental conceptual leap. It immediately explained why you needed a cold reservoir, a sink for the caloric to fall into. Without that temperature difference, the fall couldn't happen, and no work could be produced. The caloric itself, he assumed, was conserved. Just as the same amount of water goes into the top of the water wheel and comes out the bottom, the same amount of caloric was thought to leave the hot furnace and enter the cold condenser. The work was somehow siphoned off from its journey downhill. To formalize this idea, Carnot invented a purely theoretical, idealized model of a heat engine, one that operated in a perfect, frictionless, and, most importantly, reversible cycle, which we now call the Carnot cycle. This cycle involves a series of steps: an isothermal, constant temperature expansion, where the working substance absorbs heat from the hot reservoir; an adiabatic, no heat exchange, expansion where its temperature drops; an isothermal compression where it rejects heat to the cold reservoir; and finally, an adiabatic compression that brings it back to its starting point. This cycle was the ultimate gold standard. Carnot showed that any real engine, with its friction and irreversible processes, would be less efficient than this ideal Carnot engine. He had discovered a fundamental law of limitation. The inefficiencies weren't just about poor craftsmanship. They were baked into the very fabric of how heat and work relate. You could never, ever convert all the heat from your hot source into useful work. Some heat had to be rejected, wasted, to the cold sink. This was indeed the first profound, albeit unmathematical whisper of what would become the second law of thermodynamics. Tragically, as you noted, Carnot's work was almost completely ignored during his lifetime. He died during a cholera epidemic in 1832 at the heartbreakingly young age of 36. His book, all 600 copies he had paid to print, gathered dust on booksellers' shelves and vanished from libraries. It was a tragic, quiet end for a man of such genius. But the seed had been planted. A decade after his death, a French engineer named Émile Clapeyron rediscovered Carnot's work and republished its arguments, expressing them graphically using pressure-volume diagrams, which helped bring them to a wider audience. It was through Clapeyron's paper that the giants of thermodynamics in the making, William Thomson, later Lord Kelvin, and Rudolf Clausius, encountered Carnot's ideas. Now enter our next character, a German physicist and mathematician named Rudolf Clausius. In the 1850s, Clausius was building on the work of Carnot and others like James Joule, who was meticulously showing that heat and work were equivalent. You could turn work into heat, like rubbing your hands together, and in principle, heat into work, like in a steam engine. So we find ourselves in the 1850s. The world of physics is buzzing with a new, powerful idea: the conservation of energy, what we now call the first law of thermodynamics. It was a concept being pieced together by a brilliant, determined Englishman named James Prescott Joule. Now, Joule came from a family of brewers, and there's something wonderfully fitting about that. A brewer is obsessed with control, with temperature, with the transformation of substances. Sugar to alcohol, the careful application of heat. Joule, in his home laboratory, became obsessed with measuring the exact relationship between work and heat. He built a now famous apparatus. Imagine a small paddle wheel submerged in a container of water, connected by a string and pulley to a falling weight. As the weight fell, it did work. It turned the paddles, churning the water. There was no flame, no fire, no obvious source of heat. But Joule, with exquisite care, measured the temperature of the water, and he found that it rose. The work done by the falling weight was being converted directly into heat within the water. He could quantify it precisely. This was the mechanical equivalent of heat. He showed that you could rub your hands together on a cold day and warm them up. You're converting the work of friction into heat. You could strike a coin repeatedly with a hammer and feel it grow hot. Work into heat. And the reverse in principle was also true. The heat contained in the steam of an engine could, through the machinery of pistons and shafts, be converted into the work of turning wheels. This was the grand revelation. Energy is neither created nor destroyed. It only changes form. It can be potential energy in a raised weight, kinetic energy in a moving piston, chemical energy in coal, or thermal energy in steam. The total amount of energy in a closed system is constant. This was the first law, a beautiful, symmetrical, and profoundly powerful statement. It felt complete. But into this world of elegant conservation stepped Rudolf Clausius, a German physicist with a sharp, systematic mind. And Clausius looked at the first law and saw that it was telling only half the story. It was like a map that showed all the streets of a city, but gave no indication of which were one way. The first law said that all energy transactions were possible as long as the books balanced. But Clausius, and anyone who has ever left a cup of coffee on a table, knew that reality had a stubborn preference. The first law would be perfectly, mathematically content if the thermal energy in the cool air of a room spontaneously flowed into the hotter cup of coffee, making it boil over. The energy balance would be maintained. But this never, ever happens. The coffee always, relentlessly cools down. Heat always flows from hot to cold, never the other way around, unless we force it to with a machine like a refrigerator, which itself consumes energy and creates more heat elsewhere. This was the puzzle that captivated Clausius. The universe had a direction, a built-in arrow of time, and the first law was completely blind to it. There was a one-way street, and physics needed to understand the traffic sign. Clausius was building on the work of Sadi Carnot, who had intuitively grasped the necessity of a cold reservoir for an engine to function. But Carnot was working under the old caloric theory of heat, which imagined heat as a conserved fluid. Now, with Joule's work, that was overturned. Heat wasn't a fluid, it was a form of energy. So Clausius had to reconcile Carnot's brilliant insights about engine cycles with Joule's new law of energy conservation. He realized that in any real process of converting heat into work, something subtle but crucial was happening. Let's imagine a perfect, ideal heat engine, the kind Carnot dreamed of. In this frictionless, perfectly reversible fantasy, you could take a certain amount of heat from a hot source, convert some of it into work, and dump the remaining necessary portion into a cold sink, and you could theoretically run the whole cycle backwards, like a film in reverse. But in the real world, this never happens. Real engines have friction, heat leaks out, processes aren't perfectly controlled. In every real transaction, while the total quantity of energy is conserved, as the first law demands, the quality of that energy changes. Clausius saw that a portion of the heat energy was always, inevitably, degraded. What does that mean? Let's think of it in terms of usefulness. Imagine you have a single intensely hot spark. That spark has a high quality of energy. It has the potential to do something dramatic, ignite a gas, for instance. Now, imagine that same amount of thermal energy spread out evenly across an entire room. The total energy is the same, but its quality is now very low. It's just ambient warmth. You can't use it to power an engine or ignite a fire. It has become useless for doing work. This was Clausius's great insight. In any real process, energy tends to transform from concentrated, useful forms into dispersed, useless forms. When your car engine runs, the high-quality chemical energy in the gasoline is converted partly into the work of moving the car, but a huge amount is degraded into low-quality heat that is dissipated into the air through the radiator and exhaust. When you drop a ball, the potential energy is converted to kinetic energy, and when it hits the ground, that kinetic energy is converted into sound and heat, a dispersed, chaotic form of energy. The energy isn't gone, but its ability to do useful work has diminished. It's been scattered. Clausius needed a way to quantify this scattering, this degradation. He needed a mathematical measure of the unavailability of a system's thermal energy for conversion into mechanical work. He pondered this for years, refining his ideas. He understood that this tendency was what lay behind the one-way flow of heat. Heat flows from hot to cold because that is the direction that scatters the energy, that increases its disorder, that makes it less available. A hot cup of coffee and cool air represent a state of order. Energy is concentrated in the coffee. A lukewarm cup and slightly warmer air represent a state of disorder. The energy is spread out evenly. The universe moves from order to disorder. In 1865, after 15 years of work, he was ready. He introduced a new term into the scientific lexicon. He wanted a word that sounded like energy, from the Greek energeia, meaning activity or operation, but that captured this new concept of transformation and content. He reached back to the Greek word trope, which means a turn, a transformation, or a change. He prefixed it with "in," meaning in or towards. So he created the word entropy. Literally, it meant a turning towards or transformation content. He was naming the capacity for change, the potential for transformation, but specifically the kind of transformation that leads towards dispersal and disorder. With this new quantity defined, he could state the second law of thermodynamics with breathtaking scope and finality. The entropy of the universe tends to a maximum. This single sentence is one of the most profound and, for some, haunting statements in all of science. It is not a law about what can happen, like the first law, but a law about what does happen. It gives the universe its arrow. It explains why we remember the past and not the future. It tells us that in any isolated system, and the universe is, by definition, the ultimate isolated system, things will always proceed from a state of order to a state of disorder. Energy will always spread out. Differences will always even out. Think of it as the cosmic version of your room always tending to get messy. You can clean your room. You can create a local pocket of order. But to do so, you expend energy and generate disorder in the form of body heat, moved dust, etc. in the wider environment. The net effect is always an increase in total entropy. Clausius had discovered the fundamental reason why perpetual motion machines are impossible, why all processes eventually wind down, and why the cosmos has a definitive and ultimately terminal direction of time. He had identified the price of doing business in the universe. Every action, every transformation, every single event must be paid for with an increase in entropy, a step towards ultimate equilibrium, a final
this inexorable process a name.
Let's pause here and really digest what that means, because this is the core of it all. Entropy, in the Clausius sense, is a measure of this unavailability, this dispersal of energy. When heat flows from hot to cold, entropy increases. Why? Because the heat, which was once concentrated and capable of doing work, like driving a tiny engine between the coffee and the air, has now become spread out, diffuse, and useless. The energy is still there, in the warm air, but it's now in a form that is incredibly difficult to harness for any practical purpose. The universe has, in a sense, become a little more disordered in its energy distribution. Think back to our coffee and milk. Initially, you have a state of high order. The milk molecules are all in the spoon. The coffee molecules are in the cup. They are separate. This is a low entropy state. When you stir, you mix them. The milk molecules, once concentrated, are now randomly scattered throughout the entire cup. The system has become disordered, mixed up, random. This is a high entropy state, and the process is irreversible. The universe has moved from a less probable state, all milk here, all coffee there, to a more probable state, everything mixed together. There are vastly, vastly more ways for the milk and coffee to be mixed than for them to be perfectly separated. Entropy, in a very real way, is a measure of probability. It's the universe's tendency to move towards the most statistically likely arrangements. But wait, you might say, I can clean my room. I can put a refrigerator next to my coffee and make it cold again. Aren't those processes decreasing entropy? This is the most common and most crucial point of confusion. And it's where we must be very careful. When you clean your room, you are absolutely creating local order. You are decreasing the entropy inside the room, but you are not violating the second law. Why? Because the second law applies to the entire isolated universe. To clean your room, you have to expend energy. You move around, you lift things, you sweat. Your body is burning chemical fuel from your food. That process of metabolism is itself hugely entropy increasing. It involves breaking down complex, ordered molecules into simpler, more disordered waste products and heat. The heat you generate and release into the room and the air around you more than compensates for the little bit of order you created in your bookshelf. The net effect, when you consider you, the room, and the surrounding environment, is a large increase in total entropy. The same is true for a refrigerator. It pumps heat out of its cold interior and dumps it into your warmer kitchen. This seems to reverse the natural flow of heat, and it does, locally. But to do this, it needs a compressor, a motor. It needs to be plugged in. It consumes electrical energy. That electrical energy came from a power plant, which likely burned coal or gas, a process that generated a tremendous amount of waste heat and increased entropy massively. So, while the inside of the fridge gets colder and more ordered, the power plant and your kitchen get hotter and more disordered by a much, much larger amount. The overall entropy of the universe skyrockets. This is the inexorable tide of the second law. For any real process, the total entropy always increases. It never decreases. At best, in ideal, theoretical, reversible processes, it stays the same. But such processes don't really exist in our messy, frictional world. Clausius had identified the universe's one-way street. He had given a name to the reason why things wear out, why energy dissipates, why perpetual motion machines are impossible. It was a bleak but profound realization, and it was about to get bleaker and even more profound thanks to a man who would connect this abstract concept to the frantic, invisible world of atoms. So, while Rudolf Clausius was giving us the big, grand cosmic law, the entropy of the universe always increases, a quiet, parallel revolution was stirring. This was a shift in perspective, from the macroscopic to the microscopic. For centuries, scientists had treated things like gases as smooth, continuous fluids. They talked about pressure and temperature and volume as inherent properties of the substance itself. But a radical idea was gaining traction. What if a gas wasn't a smooth fluid? What if it was nothing more than a vast, unimaginable swarm of tiny, hard, perfectly elastic spheres, atoms and molecules, all flying around at tremendous speeds, bouncing off each other in the walls of their container in a frenetic, perpetual, and utterly random dance? This was the atomic theory of matter, and it was still controversial. Many respected scientists of the late 19th century, like Ernst Mach and Wilhelm Ostwald, were energeticists who believed energy was the fundamental substance of the universe and saw atoms as a convenient but ultimately unproven mathematical fiction. But a few brilliant minds began to take these tiny particles seriously. James Clerk Maxwell, the Scottish physicist who unified electricity and magnetism, was one. He started thinking about gases as collections of particles and derived the first statistical laws governing their speeds. He imagined a tiny demon, now famous as Maxwell's demon, who could, in theory, violate the second law by sorting fast and slow molecules. But it was an Austrian physicist named Ludwig Boltzmann who would take this idea and forge it into a new understanding of reality itself, one that would ultimately explain why Clausius's law had to be true. Ludwig Boltzmann was a man of profound contrasts. By all accounts, he was a passionate, volatile, and deeply sensitive soul. He was a large, strong man with a booming voice and a hearty laugh who loved nature, music, and conversation. Yet, he was plagued by crippling self-doubt, severe bouts of depression, and terrible health, including asthma and blinding headaches. He felt his work was constantly misunderstood and attacked. The philosophical opposition to atoms was not just an academic debate for him. It was a personal, profound assault on the very foundation of his life's work. He was a man trying to describe a world of chaos using the tools of order, and the chaos within him often mirrored the chaos he studied. And his insight was nothing short of genius. He looked at the second law of thermodynamics, this majestic, seemingly absolute decree from Clausius, and he asked a revolutionary question. What if entropy isn't a fundamental, ghostly, fluid-like property, as heat once was thought to be? What if it's not a thing at all? What if it's simply an emergent property? What if it's just a consequence of the statistics of countless atoms? What if the reason heat flows from hot to cold, the reason entropy always increases, is simply because it is overwhelmingly, astoundingly, almost unthinkably more probable? To understand this, we have to build a new picture of the world, piece by piece. Let's start with that box of gas. When we, as big, clumsy humans, observe this box, we describe it with what Boltzmann called a macrostate. A macrostate is the big picture description. It's defined by a few bulk properties we can measure: its pressure, its volume, and its temperature. We can say, this is a 1-liter box of nitrogen gas at room temperature and 1 atmosphere of pressure. That description, that single sentence, defines a macrostate. But what is really going on inside that box? If we could shrink down to a size where we could see individual molecules, the reality would be sheer bedlam. Trillions upon trillions of molecules, each a tiny billiard ball, are zipping around at speeds of hundreds of meters per second, colliding with each other billions of times a second. At this microscopic level, the state of the gas is not described by three simple numbers. It is described by the precise position and velocity, the exact speed and direction of every single one of those trillions of molecules. This incredibly detailed, specific snapshot of every particle is what Boltzmann called a microstate. It is the ultimate full description of the system. And here is the beautiful, crucial kicker that Boltzmann realized. A single, simple macrostate, like room temperature gas, can be realized by a mind-bogglingly enormous number of different microstates. Think about it. The macrostate room temperature just means that the average kinetic energy of the molecules is a certain value. It doesn't care which molecules are fast and which are slow. So, one microstate has molecule A in the top left corner moving fast to the right, and molecule B in the bottom right moving slowly upwards. Another, completely different microstate has molecule A in the bottom right moving slowly upwards, and molecule B in the top left moving fast to the right. From our big picture macrostate perspective, these two situations are identical. The gas has the same temperature, the same pressure. As long as the overall statistical distribution of positions and speeds is the same, the macrostate is the same. The number of possible microstates that all correspond to the same macrostate is literally unimaginably large. It's not just a big number, it's a number so vast it defies human intuition. This number is what Boltzmann called W for Wahrscheinlichkeit, the German word for probability or number of complexions. Now we get to Boltzmann's stroke of genius. He proposed that the entropy of a macrostate, the S that Clausius defined, is not a mysterious quantity, but is directly related to the number of microstates W that could produce it. He gave us the equation that is now inscribed on his tombstone. S is equal to K multiplied by log of W. Let's unpack this like we're opening a precious gift. S is the entropy, the very same thing Clausius was talking about. W is that astronomical number of microstates. K is a tiny constant, now known as Boltzmann's constant, a fundamental number of natures that acts as a bridge, translating the wild statistical world of atoms into the calm, measured world of joules per Kelvin that engineers could use. And log is the natural logarithm. Why a logarithm? Well, because the numbers for W are so insanely huge, think 10 raised to the power of 100, that we need a mathematical tool to crush them down to a human scale. The logarithm takes a number that multiplies by itself and turns it into a number that just adds up. It tames the beast. So, what does this equation mean in plain language? It is breathtakingly simple and profound. The entropy of a system is just a measure of the number of different ways you can rearrange its guts without changing its overall appearance. A low entropy state is one that is highly ordered, structured, and improbable. It has very few microstates that look like it. Think of our separated coffee and milk. There is essentially only one microstate, or a very, very small number, where all the milk molecules are in the spoon and all the coffee molecules are in the cup. That's why it's so unlikely to happen by chance. A high entropy state is one that is disordered, random, and probable. It has a gigantic number of microstates. Think of the mixed coffee. There are countless trillions upon trillions of ways to arrange the molecules such that they are all jumbled up together. The system, left to its own devices, will naturally wander through all its possible microstates. It will, statistically, spend almost all of its time in the macrostates that have the most microstates. the highest entropy states. It's not being pushed. It's just sampling the possibilities. And the possibilities are overwhelmingly weighted towards disorder. This explains everything Clausius saw, but from the bottom up. Why does heat flow from hot to cold? Imagine two objects, one hot with fast-moving molecules and one cold with slow-moving molecules placed in contact. When molecules from the hot object collide with molecules from the cold object, on average, energy is transferred, speeding up the slow ones and slowing down the fast ones. They approach an average, a middling temperature. Now, is it possible for a collision to happen where a slow molecule transfers its energy to a fast one, making the cold side colder and the hot side hotter? From the pure laws of mechanics governing a single collision, yes, it is possible. But is it probable? Think of the microstates. The number of microstates where the energy is evenly distributed, a lukewarm object, is astronomically larger than the number of microstates where the energy is concentrated in one place, a very hot spot and a very cold spot. So, the odds of the system spontaneously finding itself in that extremely ordered, low entropy state are so infinitesimally small that you could wait longer than the age of the universe and never see it happen. The flow from hot to cold is a flow from a less probable state to a more probable state. It's a flow from low entropy to high entropy. This statistical view also explains irreversibility. The laws of physics that govern the individual collisions are perfectly reversible in time. If you could magically reverse the velocity of every single atom, the movie would run backwards. The mixed coffee would unmix. So why don't we see this? Because the initial state of the unmixed coffee is a state of incredibly low probability. To get the unmixing to happen, you would need to start from a microscopically precise configuration that leads to that outcome. But there are so many more configurations that lead to mixing. So, in practice, it never happens. The arrow of time, the reason we remember the past and not the future, is this statistical tendency towards higher entropy. The past is a state of lower entropy. The future is a state of higher entropy. Boltzmann had triumphed. He had reduced a profound, seemingly mystical law of nature to a simple matter of counting. But the scientific community was slow to accept his ideas. The opposition to atomism was fierce, and Boltzmann, in his depression and poor health, felt his life's work was being rejected. In 1906, while on holiday with his family, the great Ludwig Boltzmann hanged himself. Tragically, just as he had feared his work was fading into obscurity, experimental evidence for atoms was mounting, and his theories were beginning to be recognized as the monumental achievement they were. His equation, S is equal K multiplied by the log of W, is the bridge between the microscopic world of atoms and the macroscopic world of our experience. It is his lasting, profound legacy. The story of entropy, however, does not end with Boltzmann. In the 20th century, it found a surprising new home, far from the realms of steam engines and gases. This new chapter was written by a man named Claude Shannon, an American mathematician and electrical engineer working at the legendary Bell Labs in the 1940s. So we now find ourselves in the 20th century, decades after Boltzmann's tragic death. The scene shifts from the smoke-filled lecture halls of Vienna to the pragmatic, buzzing corridors of Bell Labs in New Jersey. This was the research and development wing of the American telephone monopoly, AT&T, and it was a cradle of innovation. Here, a young mathematician and electrical engineer named Claude Shannon was working on a very practical, It seems like a fluffy, abstract concept. Is a Shakespeare sonnet more information than a grocery list? Is a scream more information than a whisper? Shannon needed to find a way to quantify it, to measure it, to give it units, just as we measure mass in kilograms or distance in meters. Without a rigorous definition, there could be no real science of communication. Shannon's genius was to realize that information is inextricably linked to uncertainty and surprise. Think about it. If I tell you something you already know with absolute certainty, I haven't really given you any new information. If I stand on a street corner in London and say, "It sometimes rains here," you would just nod and walk on. The message was highly predictable. It carried little to no surprise. But if I said, "There is a solar eclipse happening right now," that would be shocking, unexpected, a high surprise message. It carries a lot of information. This is Shannon's key insight. The information content of a message is inversely related to its probability. A highly probable message is boring and carries little information. A highly improbable message is surprising and carries a lot of information. Let's flesh this out with some fun examples. Imagine you have a magical 8-ball that only ever gives one answer, no matter how you shake it. Outlook good. If you ask it, "Will I be rich?" it says, "Outlook good." You ask, "Will it rain tomorrow?" It says, "Outlook good." After a while, you learn nothing from it. Its messages have zero surprise, zero information. Its entropy, in Shannon's terms, is zero. It's perfectly predictable, like a string of all the same letter, A. Now, imagine a different 8-ball, a fair one, that gives all its classic answers with equal probability. Yes. No. Ask again later. Outlook not so good, and so on. When you ask it a question, you are genuinely uncertain of the answer. There is surprise. Each answer carries a measurable amount of information. This source has a higher information entropy. Now let's go to the extreme. Imagine a third 8-ball that gives answers composed of completely random letters, X, Q, J, R, P, L, Z. This is the most unpredictable source of all. Every single message it produces is a total surprise. It has the highest possible information entropy. There is no structure, no pattern, no predictability, just pure random noise. Ironically, this chaotic jumble, while high in information content, is completely useless for communication because it lacks meaning. This is a crucial point Shannon made. Information theory deals with the amount of information, not its meaning or truth. A beautifully crafted lie and a scientific fact can have the same information content if they are equally surprising from the perspective of the source. This is where the magic happens, and where Shannon's story collides with Boltzmann's. Shannon needed a mathematical formula to measure the average uncertainty, or surprise, of a message source. He was considering a set of possible symbols, like the 26 letters of the alphabet plus a space. Each symbol has a certain probability of appearing. He wanted a single number that captured the overall unpredictability of the next symbol in a sequence. He laid down a set of logical properties this function should have. It should be continuous. It should increase when the number of possible symbols increases. It's more uncertain to guess a letter from a 26-letter alphabet than from a 2-letter alphabet. And most importantly, it should be additive. If you receive two independent messages, the total information should be the sum of the information in each. As he worked through the math, a familiar form emerged. The only function that satisfied all his criteria was one that looked exactly like Boltzmann's statistical entropy. The average information, or the information entropy, H, for a set of symbols with probabilities P1, P2, P3, and so on to Pn was minus P1, the log P1, P2, the log of P2, and so on to Pn, the log of Pn. Let's breathe life into this equation. The p-values are the probabilities. The log is again the logarithm, which here beautifully converts the probabilities of independent events into additive information. The minus sign is just there to make the final value positive, since logarithms of probabilities, which are between 0 and 1, are negative. Now for the naming. The famous anecdote which Shannon himself confirmed is that he asked the brilliant and witty mathematician John von Neumann for advice. He said something like, "I have this measure of uncertainty in my communication theory. I don't know what to call it. It's already in use in statistical mechanics, and it's basically the same form." And von Neumann, with his characteristic sharpness, reportedly replied, "You should call it entropy. First, because that's what it is in statistical mechanics. Second, and more importantly, nobody knows what entropy really is, so in a debate you will always have the advantage." It was a joke, but it contained a deep truth. Shannon took the advice, and information entropy was born. The connection was far more than a clever name. The mathematical form was identical because the concepts were deeply analogous. Let's line them up side by side. Boltzmann's entropy, S is equal to K multiplied by the log of W, measures the number of ways, microstates, a physical system can be arranged while still looking the same from the outside, macrostate. High entropy means many possible hidden arrangements, high disorder and randomness. Shannon's entropy measures the number of possible messages a source can produce while still conforming to its statistical structure, e.g., letter frequencies. High entropy means many possible surprising messages, high unpredictability. Boltzmann's W is about the number of hidden physical configurations. Shannon's H is about the number of hidden message sequences. In both cases, entropy is a measure of missing information. To fully describe the system's microstate, or to precisely predict the next symbol in the message, you need a lot of information. A high entropy system, a hot gas, a random text, keeps its secrets well. A low entropy system, a ice crystal, a repetitive slogan, is an open book. This connection is not just a neat mathematical coincidence, it is profoundly physical. Shannon's work implied that information is not a disembodied abstract idea. It is always tied to a physical substrate. A bit of information, a 0 or a 1, isn't a Platonic ideal. It is a switch that is either on or off. It is a pit or a land on a DVD. It is a north or south magnetic domain on a hard drive. It is a neuron that either fires or doesn't. Information is made of stuff. And because it is physical, manipulating it must have physical consequences, governed by the laws of thermodynamics, especially the second law. This profound implication was fully realized by another IBM researcher, Rolf Landauer, in 1961. Landauer asked a simple, devastating question: what is the minimum energy cost of a computation? He focused on a fundamental, irreversible operation, erasing a bit of information. Think of a single computer memory bit. It can be in one of two states, 0 or 1. Before you erase it, it has some uncertainty. It could be either. This corresponds to a certain number of microstates for the physical system representing the bit. When you command the computer to erase that bit, you are forcing it into a specific known state, say 0. You are reducing the number of possible microstates for that physical system. You are, in Boltzmann's terms, decreasing its entropy. But the second law of thermodynamics forbids the total entropy of the universe from decreasing. So, for this local decrease in entropy, the erasure of information, to be possible, there must be a compensating increase in entropy somewhere else. Landauer showed that this compensation takes the form of heat dissipation. Every time you irreversibly erase one bit of information, you must release a tiny but fundamental and unavoidable amount of heat into the environment. This is Landauer's principle, and it sets the ultimate lower limit on the energy consumption of any computer. It forges an unbreakable link between the world of information and the world of physics. When you clear your browser history or delete a file, you are not just moving abstract ones and zeros. You are causing a physical transformation that, at a microscopic level, generates heat and increases the entropy of the universe. Your computer, in a very real sense, is a heat engine, and the fuel it burns is randomness, which it converts into ordered computation and exhausts as disordered heat. So the journey of this one concept, entropy, is a story of convergent intellectual evolution. It began with Clausius, who saw it as the dissipated, wasted heat in an engine, the cosmic tax on doing work. Boltzmann then peered deeper and saw it as the hidden disorder, the statistical weight of countless possibilities. Finally, Shannon, thinking about phones and radios, rediscovered it as the very essence of surprise and information, a measure of what we don't know. 3 different paths, leading to the same mathematical peak, revealing that the flow of heat, the tendency toward disorder, and the transmission of knowledge are all threads in the same fundamental fabric of reality. It is the mark of a concept so deep that it was waiting to be discovered in the noise of the world, not just once, but again and again. Now that we have these 3 powerful lenses through which to view entropy, the thermodynamic, the statistical, and the informational, let's use them to explore its role in the world around us, and ultimately, in the cosmos itself. Let's start close to home, with life. A living organism seems to be the ultimate argument against entropy. A human body is a marvel of order and complexity. We take in disordered, simple molecules from our food, and we assemble them into intricate, highly structured proteins, DNA, tissues, and organs. We maintain a constant internal temperature in a changing environment. We grow, we reproduce, we create art and buildings and cities. All of this seems like a massive local assault on the second law. Is life a violation? Absolutely not. Life is a spectacular example of a localized, sustained, low entropy state. But it is a state that is paid for, and paid for handsomely, by a massive increase in entropy elsewhere. The biologist Erwin Schrödinger, in his famous book, What is Life?, described living organisms as feeding on negative entropy, or negentropy. They maintain their internal order by sucking orderliness from their environment. Let's trace the flow. The primary source of negative entropy for almost all life on Earth is the sun. The sun is a massive, high-temperature, low-entropy reservoir of energy. It is a gigantic ball of fused hydrogen, a state of incredible energy concentration. This energy radiates out into the cold, vast emptiness of space. As it travels, the radiation is diluted. The photons spread out. The entropy of the sunlight increases enormously by the time it reaches Earth, but a tiny fraction of this energy is intercepted by our planet. Plants, through the miracle of photosynthesis, capture this high-energy, low-entropy sunlight and use it to drive chemical reactions. They take simple, high-entropy molecules like carbon dioxide and water, and using the sun's energy, build complex, low-entropy molecules like glucose and other carbohydrates.
carbohydrates.
They are, in essence, using the sun's energy to pump entropy uphill locally, creating order within their cells. They release waste oxygen and a little heat in the process, increasing the entropy of their immediate surroundings. Then, animals like us come along. We eat the plants, or other animals that ate the plants. We break down those complex, ordered carbohydrates and fats. This process of metabolism is a controlled, step-by-step burning. We oxidize the food, breaking it back down into simple carbon dioxide and water, the same high-entropy waste products. In doing so, we release the stored solar energy to power our own bodies, to build our own proteins, to think, to move. But the vast majority of the energy is released as heat, a high-entropy form of energy. We are, in effect, taking the order created by the plant and dissipating it as heat, all while maintaining our own internal structure. So, the overall process is the sun's core, very low entropy, sunlight traveling to Earth, entropy increasing, photosynthesis, local entropy decrease in the plant, metabolism, local entropy decrease in the animal, but a huge overall entropy increase as waste heat and simple molecules are produced. The magnificent cathedral of life is built and maintained by the relentless torrent of entropy flowing from the sun. We are like eddies in a river, temporary patterns of order that persist only because the river of energy and entropy is flowing through us. The second law is not violated. It is the engine that drives the complexity of life. Without this global entropy production, life would be impossible. This brings us to the grandest stage of all, the cosmos. What does entropy have to say about the beginning and the end of the universe? Modern cosmology presents us with a profound puzzle, often called the entropy problem. We look out at the universe today, and it is, for the most part, a fairly high entropy place. Stars are burning out, heat is dissipating, matter is spreading. But it's not at maximum entropy yet. There are still concentrations of energy like stars and galaxies. However, when we look back in time, to the very beginning in the Big Bang, we find something shocking. The early universe was an incredibly hot, dense, and, this is the key part, unbelievably smooth fireball. The cosmic microwave background radiation, the afterglow of the Big Bang, shows a universe that was almost perfectly uniform in temperature. There were only tiny, tiny fluctuations. From our understanding, a smooth, uniform state is a state of very high entropy for a gas in a box. So why was the early universe in such a low entropy state? A smooth, hot soup of particles is the most probable highest entropy state for gravity? No. This is the crux of the matter. The early universe was not in a high entropy state when gravity is taken into account. Gravity changes everything. For a system dominated by gravity, the high entropy state is not a smooth, uniform distribution. It's the opposite. The most probable state for a gravitational system is one where matter has clumped together. A star, for instance, is a massive entropy-producing engine. It starts with a diffuse cloud of hydrogen, relatively low entropy for gravity, and collapses under its own weight. As it collapses, it heats up and eventually ignites in nuclear fusion, pouring out high entropy radiation for billions of years. The end result, a black hole, is, according to our best theories, the single highest entropy object possible for a given amount of mass. So, the early universe was in a state of phenomenally low gravitational entropy. It was smooth when it wanted to be lumpy. This is the ultimate low entropy starting point that sets the arrow of time for the entire cosmos. Why the universe began in this spectacularly special low entropy state is one of the deepest unanswered questions in physics. Some point to cosmic inflation, a period of hyper-expansion in the first fractions of a second, which would have stretched the universe into smoothness. Others ponder ideas of a multiverse. We simply don't know for sure. But we can project the future. The second law tells us the universe is on a one-way trip to a state of maximum entropy. This is known as the heat death of the universe. It's a misnomer. It's not about heat in the sense of high temperature. It's about thermal equilibrium. Imagine all the energy in the universe has finally finished flowing from high places to low places. All stars have burned out, their ashes scattered. All black holes have, over almost unimaginable timescales, evaporated via Hawking radiation. The universe becomes a thin, ever-cooling soup of fundamental particles and radiation, spread perfectly evenly across an ever-expanding void. There are no more temperature differences, no more concentration gradients, no more free energy to do any work. It is a state of maximum entropy, a final, eternal, and uniform stillness. Every process will have ceased. It is the ultimate triumph of disorder, the final quiet conclusion to the story that began with a mysterious low entropy bang. From the practical worries of 19th century engineers to the ultimate fate of all existence, the concept of entropy has proven to be one of the most powerful, pervasive, and profound ideas in all of human thought. It is the reason time has a direction, the reason life is possible yet finite, the reason our memories are of the past and not the future. It is the hidden cost of every action, the silent partner to every transformation. When you light a candle, when you breathe, when you think a thought, you are participating in the great cosmic exchange, trading order for disorder, and in doing so, writing a tiny part of the story of the universe's journey from a mysterious beginning to a quiet, final end. It's a humbling concept, but also a unifying one. It connects the steam in an engine to the thoughts in your brain, the fusion in a star to the growth of a tree. It is, quite simply, the law of decay and the price of structure. And now, you know its story. You've seen it from every angle. The next time you see your room get messy or your coffee go cold, you can smile and know that you are witnessing a tiny, local expression of the most fundamental and relentless law in the cosmos. Good night. Have a deep, calm sleep.